Let's talk about security data sets. My name is Octavian Suciu, and today I'm going to talk about when does machine learning fail. So this work couldn't have been possible without my collaborators Radu and Idjan, as well as professors Hal Daume and Tudor Dumitras from University of Maryland. In machine learning, we want to train a classifier. We start from a bunch of labeled examples. For example, we might have benign and malicious Android applications, and we use an algorithm in order to learn a decision boundary which would separate those examples. Then we want to test the classifiers on new and unlabeled examples, and we use the decision boundary in order to predict the labels of these unknown examples. Adversarial machine learning looks at situations where the attacker might want to subvert such a classifier. So for example, an attacker might want to misclassify a malicious Android app as benign through the malware detector. So the literature looked at lots of attacks and defenses and all make various assumptions about the capabilities of the attacker. And in this paper, we want to evaluate what is the practical impact of assumptions on the success rate of such attacks. And by doing so, we might be able to have some interesting design decisions for future defenses. So let's look at a practical example of a classifier. We're looking at the Drebin Android classifier, which was previously published, and it uses a support vector machine classifier and is trained on a public data set. All right, so an attacker might use evasion attacks, as we've previously seen in the previous talk. Evasion attack, the attacker has a target, a malicious target, and they want it to be misclassified as benign. So the evasion attacks just modify the target features in order for it to cross the decision boundary. But if the attacker does not want or is unable to modify the target features, they might resort to data poisoning attacks. And fortunately, our keynote speaker made my job easier here, so we already saw a famous data poisoning attack. This is Microsoft TAE chatbot, which was poisoned by users on Twitter. But let's look at a data poisoning attack on our Drebin classifier. So again, we have the testing time target, and we want it misclassified. So the attacker, if they are able to modify the training set, they might easily just insert the target with the flip label into the training set, so that at test time, when the instance is seen by the victim, it will be misclassified as benign. However, this has the assumption that the adversary has control over the labeling function of our victim. But let's look at how Drebin performs the labeling. So Drebin just takes the Android applications and submits them to VirusTotal. VirusTotal is an online platform which has multiple AV vendors, and based on a detection ratio, which looks at all the AV vendors, returns the maliciousness of a file. So Drebin actually uses this score in order to attribute the benign or the malicious labels. And in fact, I'm going to show you later in this talk that we could design a targeted poisoning attack. We call it StingRay, that achieves the poisoning goals without requiring access, without requiring labeling capabilities. So now let's look at the attacker limitations through the lens of existing attacker models. All right, so first of all, the attacker might have a surrogate training set. Some instances of the victim might be known, some might not. And using this training set, they might build their own classifier and perform their attack strategy using it. Then we have black box attacks. We saw in the previous talk. The attacker has query access to the victim, and they do not know much more. And then we have white box attackers, which have complete information about the victim. And by now, I'm pretty sure you're already convinced that those do not hold well in practice. Let's look how they work on Drebin. So on Drebin, we have a known and publicly available training set, so we have complete and full instance knowledge. We also have a guessable classifier. We know it's a support vector machine. Some parameters, although, are unknown. So we have partial algorithmic knowledge. And those could be easily captured by existing models. And in fact, prior work looked at this measure of transferability, which measures how much an attack would succeed on the victim if it is crafted on a surrogate attacker classifier. All right, but let's look at the features involved in malware detectors. So malware detectors usually use program analysis features that are usually such as the ones derived from code disassembly, static and dynamic analysis features, and Android, the Debian classifier is no exception, besides using some meta features, such as permissions from the Android manifest. It also uses some static analysis features such as API calls or URLs. And it's actually unreasonable to assume that the attacker might know or modify or be able to modify all those program analysis features. So this leads us to some interesting limitations here. So proprietary feature from binaries, program analysis features might lead us to a partial feature knowledge, and also hard to modify features might lead us to partial leverage on the attacker side. And these two dimensions cannot be captured using the previously mentioned attacker models, and in fact they all make the same assumption, that is, the attacker has full knowledge and full leverage on all those features of the inputs. All right, so what's the impact of this problem? We're going to look at the StingRay attack that I'm going to present later, and we're going to look at the success rate of the attack, meaning how many attacks are actually successful on the victim. And here, if we have implicit full knowledge assumed, we see that in the white box case, the attack achieves around 50% success rate. If we model an attacker with 10% training set knowledge, we see that existing models allow us to observe the success rate of the attack gets reduced to around 25%. However, if we look at the practical limitations on the leverage side, meaning the attacker cannot modify the program analysis features, we see that existing models overestimate the success rate of attack by 36%. And using that assumption, we see that hiding 90% of the training set decreases the success rate of the attack by half. So our contributions are as follows. We propose the failed adversarial model for looking at realistic adversarial capabilities along multiple dimensions: features, algorithms, instances, and leverage. Using those realistic assumptions, we model StingRay, which is a generic poisoning attack, and we implement it against multiple applications and defenses. And finally, with this in hand, we perform a systematic evaluation of how much the adversarial success rate depends on implicit assumptions. And this allows us to come up with more accurate threat assessments for future. All right, so I'm going to take each one of those in turn. The fail model looks at adversaries with variable knowledge and capabilities levels across features, algorithms, instances, and leverage. What does this mean on Debian? We saw before we have partial feature knowledge, we have partial algorithmic knowledge, we have full instance knowledge, and we have partial leverage. All in all, those 4 dimensions define our fail adversary, and using those 4 dimensions, we could generalize the notion of transferability to look at attack success rate under those realistic assumptions. All right, so how do we reason about the feature knowledge of the attacker? Here we want to see how much the attacker knows about the victim features. Maybe some features such as those extracted using program analysis could be kept secret, or maybe some of their values, so some of the exact values of features might be unknown. For example, imagine a victim that decides to release a lower resolution of an image data set so that the attacker might not know the exact pixel values for some images in the training set. On the algorithmic side, we want to look at the degree of knowledge about the victim classifier. So here, the attacker might have white box access, full knowledge about the victim, or black box access, or they might just know some partial information. For example, the attacker might just know that the victim uses a convolutional neural network, but the exact architecture might be unknown. On the instances dimension, we measure the overlap between the attacker and the victim training sets. So here, we might have public data sets. Images are well known for that. All the classifiers are trained on publicly available data. Or instances might not, like public instances, might not even be sufficient, sizable enough for the attacker to train a robust classifier. For example, malware, publicly available malware datasets are known for that. All right, finally, on the leverage side, we want to limit the crafting capability for the attacker. So we might have some features that the attacker might not be able to modify, for example, program analysis features, or we might have unintended side effects when modifying some features. So the attacker, if we have a watermarked image, by modifying some pixels in the image, the attacker might break the integrity of that image. All right, so using all those considerations, we are going to look at how to design a targeted poisoning attack that works on multiple applications. And in fact, we looked at 4 target applications. We looked at Drebin, which I talked about. We look at the convolutional neural network, which achieves performance comparable to other evasion studies that were against image classifiers. We look at a previously published Twitter exploit detector that uses an SVM classifier. And finally, we look at a data breach predictor based on random forests and time series-based features. So targeted poisoning is actually hard. Let's see why is that. So let's see that the attacker has the target. They want to have it misclassified. And as we saw before, they might just want to switch the label of the target and insert it in the training set. However, it is unreasonable to assume that the attacker controls the labeling function of any instance. Nevertheless, the target. All right, so the attacker might get smarter about the way they craft instances. So what they do is they just craft instances with the opposite label, in this case, malicious applications, and when inserted in the training set, those instances will end up shifting the decision boundary of the victim so that the target gets misclassified as benign. All right, so by doing this, we actually observed that existing defenses might detect such instances as outliers, and because outliers will be removed later on, the success of the attack will decrease substantially. All right, so the attacker, of course, has to be more careful about the way they craft instances, and now they bypass outlier detection, and they successfully shift the decision boundary of the classifier. And at testing time, of course, the target is misclassified, but what we observed is that besides the target being misclassified, we had some unintended collateral damage, meaning indiscriminate damage on the victim that is, again, detectable by the victim when testing the classifier. All right, so what our attack achieves and what a general targeted poisoner would want to achieve is this Goldilocks scenarios where the poisoning instances are just sufficient to shift the decision boundary of the classifier on the victim. And in fact, StingRay achieves both individual and collective inconspicuous through the crafting procedure. So to recap the requirements for such an attack, we don't want to assume control over the labeling function. We don't want our samples to be inconspicuous, and we want to adhere to the practical fail considerations. So high-level illustration of how StingRay works. We have the target, and we choose base instances. Base instances are instances that already exist in the training set of the attacker, and they're used to craft poisoning instances. So the crafting works by just modifying the base instances to add features from the target, and therefore they would shift the decision boundary. And at test time, of course, those poisoning instances would result in the desired targeted misclassification. All right, so let's look at the attack from the features perspective. When we submit a Drebin sample, Android sample to VirusTotal, to the labeling function, we observe that VirusTotal highlights some features as more suspicious than others. For example, write contacts is more suspicious than reading the Wi-Fi state. All right, so then we could choose benign applications, opposite label applications, that are somewhat similar to the target in terms of features. So note here that the similarity is not necessarily in terms of the most suspicious features as determined by the oracle. And then we just copy those applications over for crafting purposes, and by doing so, we actually reuse existing benign functionality, and we could mitigate the lack of leverage on features that come from program analysis. And we modify the samples by just inserting small perturbations, meaning we add features from the target to the crafted instances. And again, those need not be the most suspicious ones. And by doing so, we are able to bypass existing defenses. We looked at 3 defenses against targeted attacks, including one that we had to adapt to account for targeted poisoning. I encourage you to look more in the paper for this analysis. All right, and finally, how do we ensure the labeling of the crafted instances? Well, the answer is we don't. So we just have to use the exact same label that was used by Drabin. And we, in fact, crafted 19,000 applications. And we submitted them to VirusTotal, and 89% of them got labeled as benign, like showing that this approach is viable. All right, so by now you might want to ask yourself, how is this applicable to neural networks or other end-to-end learning approaches which don't really have the concept of features? So those approaches just learn the features from raw data, such as image pixels, and there's an extensive body of work on evasion attacks, and we might just use an existing evasion attack for poisoning. For crafting the poisoning instances. And that's what we try to do. We try to take GSMA, which is a well-known evasion attack, and we try to craft poisoning instances with it. And we soon observe that this leads to very large indiscriminate damage, so a lot of collateral damage. And that's because GSMA pushes instances towards the target class. And we are actually interested in pushing instances towards a target instance. So that's what we do. We have to modify GSMA's objective function in order to move the poisoning instances towards the target. And we actually we actually evaluate StingRay on all 4 applications that I talked about. I'm not going to go into details in the interest of time, but you could find all the results in the paper. All right, so now how could we do the fail evaluation in practical scenarios? We take Drabin, for starters. We look at a full unconstrained attacker. We also look at an attacker limited that knows 20% of the features, that knows another like linear algorithm, or has like limited training set knowledge, or is just able to modify features that do not come from program analysis. And we observe that the success rate of Drabin generally gets decreased on all dimensions with limited knowledge. However, we saw that some attacks that are perceived as failed on the attacker are in fact successful when delivered on the victim, and this proves that the success rate of an attack is not really linear in terms of the attacker capabilities. And we also observed that feature secrecy constantly appears to be the most powerful limited factor against targeted poisoning attacks on this application. So that might be viable for future defenses to look at. All right, and on images, by modifying GSMA, we are able to actually put GSMA and StingRay side by side. And again, we look at an unconstrained attacker, one that only knows the center of an image. We crop a border around the image that is not known to the attacker, one that has like a different CNN architecture, one that is limited in terms of training instances, and again, an attacker that cannot modify pixels that around a border of an image. And we see that StingRay remains pretty much successful on all dimensions. Sometimes on the leverage dimension, the success rate even gets higher because the limited leverage results in a more constrained attacker that is actually able to more successfully localize their crafted strategy. And we see that although the GSMA attack is more effective on the white box case, it generally fails on all other dimensions. And this is pretty much in contrast to prior work that look at the transferability on the A dimension. And we have an interesting discussion on what this might be the reason for it. But basically, we believe that there's some sort of implicit assumptions on the instances side of prior work that look at the GSMA transferability. All right, so before I conclude, I just want to mention that fail allows us to capture attackers and defenses proposed in prior work. And I'm not going to go into details here, but basically we look at both test time attacks and training time attacks, and we see how all the 4 dimensions that I introduced in this paper could be captured across those attackers. So in conclusion, we could model realistic adversarial assumptions using fail, and we could also look at existing attacks, and we could generalize the notion of transferability that way for both evasion and poisoning attacks. And using those practical assessments, we are able to design StingRay, a targeted poisoning attack that is effective against more applications and does not assume control over the labeling function. All right, so we're trying to make the fail framework available for other attacks beyond StingRay. We're tirelessly working to support clever Hans and existing evasion attacks to look at their transferability. This is pretty much still work in progress, but we're tirelessly working on it. So please check out the Git repo and subscribe for our updates coming soon. So thank you very much, and I'm going to take questions now.
Okay, so while people walk up to the mic, could you comment on whether these dimensions you speak of, whether they have other aspects? So, for example, the leverage dimension, one may think, okay, the attacker can control maybe few number of instances or a more number of instances. Are there other aspects that might be inside these dimensions?
Right. So, what we observed is that some of the aspects are pretty much like application dependent, and for example, the things you mentioned are only applicable to poisoning attacks, right? If you are looking at evasion, you're interested only in the feature dimension. So, I guess we also had a discussion about some constraints on the attack. We wanted to look at the L dimension and more crafting capabilities for the attackers in terms of modifying the features, right? So I think it's interesting for future work to look at how we could more quantify those aspects and see what the effect of such quantifications would look like. Yeah.
Okay, I guess I'll ask one more. So is there a hierarchy between the dimensions? So is it easier for attackers to kind of compromise one dimension, and is it or harder for certain other dimensions? So is there kind of a structure to these dimensions?
I guess the best answer again, for this is it depends. We observed that on Drebin, features seem to be super important capabilities for the attack success. Right, but when you look on image classifier on neural networks, that is not the case. So I think it really depends on the feature representation and the sparsity of the data sets used for training, as well as it seems to me that there's some sort of tipping point in terms of the resources required by the attacker in order to achieve their success to some extent, right? So I think that's definitely interesting to explore further.
Hi, I'm from the University of South Florida, and thank you for the sharing of your work. And I have one small question about at the beginning of the slides, you said that you need to train a classification hyperplane, as I have known that in the deep neural networks we actually don't have this kind of hyperplane, right? So when you build your own attacking model, do you have your own surrogate model or like that, or you just use as the previous paper have said, they use the teacher model?
I'm not aware. What's that model?
I mean the attack model you have used to attack the targeted neural networks. You built your own model, or you just use the teacher model?
So just to make clear, the intro was just an example of how things work on the SVM-based malware classifiers. So I'm pretty sure I could have exemplified that better on neural networks. Yeah, I guess we're using the surrogate model, which is the best effort given all the resources available to the attacker, right? So we might just know that we have this architecture, but that knowledge might not be what the teacher, I mean, in this case, the victim uses, right? So it's just best effort with what resources.
So how did you craft the adversary report? You just based on the target model, or you?
So the instances that we craft, like the attack has some success considerations. If it fails on the available classifier, the poisoning instances will just be thrown away, right? So the attack would not be triggered. But the ones that the attacker perceives as successful would just trigger it on the victim as it would have in the original application, right? So, and then that's how we measure the success rate I showed in all the slides.
Okay. The second problem is question I want to ask is, as you have said, you tried the GSMA. Have you ever measured the time cost about this algorithm? The time cost, the time.
Oh, the time.
Yes.
Actually, we were surprised to find out that our optimization is faster than the GSMA, because we don't involve the Jacobian-based optimization, which is quite expensive in GSMA. So what we do is we compute the gradient of the crafted instances with respect to the target, and that's how we perform it. And we also do this computation within the hidden layers of the neural networks, whereas GSMA does it on the last layer before the softmax. So this saves quite a lot. I don't have exact numbers, but there's a discussion on it in the paper. So.
Okay, thank you.
Yep.
So let's thank the speaker once again.
Thank you.